Hello everyone. In this video I'm going to go over the Math-108 homework on expected value. So for the first set of questions here, consider the experiment of drawing one card from the standard deck. If the card is an ace, you'll win $20. If the card has a number, 2, 3, 4, 5, 6, 7, 8, 9, or 10, you'll win that many dollars. If the card is a face card, you'll lose $5. Fill in the table below with the probability of each amount that it is possible to win. I put win in quotes here because one of these values is a negative, representing that you're actually losing $5, not winning $5. All right, so the probability of getting $20, so that's for aces, right? And there are 4 aces in the deck out of 52 cards in the deck, so that's 4 out of 52. $2, you would have to draw a card with a 2 on it, so again, there's 4 of those out of the 52 possible. And in fact, for all of these, except for the last one, these are all going to be 4 out of 52 because there are 4 cards of each rank. Now for the last one, this is what happens if you get a face card. So we need to think about how many face cards there are in the deck. So face cards are jacks, queens, and kings. They literally have people's faces printed on them. So there are 12 of them in total. If we were to add up all these probabilities here, they should all add up to 1. So you could check that if you wanted to. Now for number 2 here, what is the expected value for the amount 1? I'm going to add a column to this table that is going to make this easier to calculate. So I'm going to put a third column here that is amount times probability, and I'm going to multiply together these numbers in each row. And then what I'm going to do is I'm going to also put another row here, and then I'm going to total it at the bottom. And that total will be the expected value. Okay. So $20 times 4 over 52. When you multiply a fraction times a number, that number gets multiplied into the numerator, not the denominator, and certainly not both. So 4 times 20 is 80, so this will be 80 over 52. So I'm just multiplying each numerator here times the amount over here, and then I'm going to leave it as over 52. That way when I add it up at the end, it'll be some big number over 52, and I can just put that into a calculator. Okay, so 2 times 4 over 52 is 8 over 52. 3 times 4 is 12. That's also over 52. 4 times 4, 16. 5 times 4, 20. 6 times 4. This is not very interesting so far. Just going through all of these. 8 times 4. 9 times 4. 10 times 4. Okay, the last one's a little trickier. 5 times 12, that is 60. Oh, and this is also negative right here. So this last one, make sure you keep the negative on there. Okay, so I've got all of the amounts times their probabilities, and then I'm just going to add all of those up. And I'm really just adding the numerators because I know they're all over 52, so the result here will also be over 52. Okay, so I'm just going to grab a calculator, and I'm going to do 80 plus 8 plus 12 plus 16 plus 20, 24, 28, 32, 36, 40, and then the last one is negative, so I'm going to subtract 60. All right, so I'm getting 236, and they all had the same denominator, so that is still the denominator of the total. And now I'm going to actually put that into the calculator and divide 236 over 52. So I'm getting 4.5. If I round this to a dollars and cents amount, this should be $4.54. $4.54. So the reason I did it this way with keeping them all over 52 is if you round on each and every single one of these ones here, then when you add them up, your rounding errors also get added up. So if you only have to round on one step, that's going to give you a more precise answer. It's not a huge deal, but it would be a better answer. Okay, so I'm getting, for the second question here, that is the answer that I'm calculating from the table there. Okay, now the last question in this section, if you play the game 100 times, how much money would you expect to win or lose in total? So you're expecting to win this much, 454, on each game on average, so you would just multiply that by 100. So you're getting that much on average 100 times. So we're just doing 454 times 100, and I guess I could keep a couple more decimal places from my calculator answer here, but if you hadn't kept them, then you'd be getting 4540. If you did keep a few more decimal places, you could get a more kind of precise answer, 453.84. But either way is fine. Obviously, if you're running your own actual casino, you probably want the answer that is the most precise. So maybe I will back up and do this. This is 236 over 52. And then if I were to chuck that into a calculator, I would get this more precise answer here, 453.84. Okay. But 454, oh no, I'm sorry. Yeah, $454, sorry, is what you'd get if you just multiplied this rounded version by 100. And that's what you would get if you rounded this answer to dollars. But either one is okay, unless I specify a number of digits to round it to. Okay, let's look at the next expected value problem here. You are running a carnival-style game for a charity fundraiser. In this game, players dig for treasure in a sandbox, which is divided into the grid shown below. So this is our sandbox, and it's in a 5x5 grid. Only one square of the grid can be searched per game. So the idea is they give you a little shovel, and then you go dig and see if there's anything in your square. The white squares contain nothing, the gray squares contain $1, and the black squares contain $5. Assume that each square is equally likely to be chosen. So basically the players don't know they don't have this chart, so they don't know what's in each square. Find the probability of winning the amounts listed below. So you can either get nothing, or if you get a gray square, you get $1, or black square is $5. Okay, so if each square is equally likely, how many squares give you nothing? So actually, I think it's easier to count the ones that do give you something first. So the black squares give you $5, and there's only 3 of those. So that's going to be a 3 out of 25 probability because there's 25 squares in total. The gray squares are giving you $1. So let's see, there's 1, 2, 3, 4, 5, 6, 7, 8 of those. And then the rest of them should be white. So this was 11 squares together out of 25. So I think 14 should be white. We could also count, but it should be right. Okay, so then once again for number 5, I'm going to expand this table with another column. I should have just done it to begin with, but oh well. Another column and another row, and I'll do it the same way I did before. So this will be amount times probability, and then I'm going to total it at the bottom. Okay, so $0 times anything is going to be 0. $1 times 8 over 25, when you multiply something by 1, nothing happens, same number. And then for this one here, multiply that 5 into the numerator. So that's 15 over 25. Now we're going to add these up. We can forget about 0, adding that doesn't do anything. So 8 over 25 plus 15 over 25. 8 plus 15 is 23. So this is 23 over 25. And then we can put that into a calculator. Oops, that's not how you spell it. Oh, let's try that one more time. My little squiggly equal sign, which means I'm going to round. So 23 over 25. Oh, actually, I guess I don't need to round. So this is an exact answer of, oops, not that one, 0.92 or 92 cents. So this is the average amount that we would win from playing this game over and over and over, assuming that they reset the squares every time before we play again. Otherwise, we would not be able to play it more than 25 times. Okay, so that was the answer here. And then for number 6, you figure you can get 100 people to play this game, and you want to get at least $200 in profits. How much should you charge to play the game? Okay, so you're doing this charity fundraiser, you want to get $200. You think you can get 100 people to play. How much do you need to charge them? So what you've got to figure out here is how much do you need to profit per game? So if you need $200 in profits and you think you can run the game 100 times, then how much do you need to profit per game? So if we want 200 total and we want that over 100 games, we need 200 divided by 100 or $2 per game profit. Okay, so if I'm going to profit $2 per game, what do I need to charge these people? Because I've got to pay them 92 cents in prize money on average. So if I'm giving everybody 92 cents on average and I need to profit $2 from them, what do I need to charge them? Just add $2 to this amount of money. Charge them their own prize money and then charge them $2 extra. Okay? Charge them their own average prize money. They pay for their own prizes. And also $2 profit. Okay? So the total you should charge them is $2.92 per game, or really you should probably round up to $3 if you're really going to do this, because $2.92 is weird. Okay, the last section here. A bag contains 10 poker chips. 5 are white, 3 are red, 2 are blue. White chips are worth 1 point each, red chips are worth 5 points, and blue chips are worth 10 points. I think this is the correct amounts that people usually use. It's been a while since I played poker. Fill in the table below with the probability of each amount you can get by reaching into the bag and taking out 1 chip. Okay, so how many total? We have 10 chips total, so these are all going to be out of 10. And then 1 point is for white, so basically there's 5 white, so 5 out of 10. I'm going to leave this as 5 out of 10 just for the sake of when I do that extra thing, so that everything has the same denominator, right? That'll make it easier. Just leave them out of 10. Okay, 5 points is for the red ones, so that's 3 out of 10. 10 points is for the blue, there's 2 of those. Okay, so now I'm going to do points times probability. So 1 times 5 out of 10 is 5 out of 10, 5 times 3 out of 10, 15 over 10, 10 times 2 over 10 is 20 over 10. Again, I could simplify these, but just going to leave it like this so it's got the same denominator. Total. So my total here, 5 plus 15 plus 20 is going to be 40, and that's over 10, and that's going to be 4. Okay, so my expected value here is 4 points for taking 1 poker chip out of the bag. All right. Probably if I give you a quiz, I don't expect you guys to have calculators, so I would make it pretty easy like this, or I would tell you to bring a calculator, one or the other. Number 9 here. Fill in the table below with the probability of each amount you can get by reaching into the bag and pulling out 2 chips in order without replacement. Be careful with the probabilities for 6 points, 11 points, and 15 points, as there are 2 ways each can happen. Yeah, so let me explain this a little bit more. So what are the things that can happen? You can get 2 white chips, that's 2 points. If you get a white and a red, that's 6 points. But you could get the white first, or you could get the red first. That's what I mean by 2 different ways. 10 points would be if you got 2 red. 11 points would be, let's see, that'd be 1 plus 10, so that would be white and blue. 15 points, that would be red and blue. So again, it could be red-blue, or it could be blue-red. 2 ways that could happen. And then 20 points would be 2 blue. Okay, so how do we calculate these probabilities? We're doing this in order without replacement. So, sorry, this table is just bugging me. Oh, okay, there we go. All right, so how do we get these probabilities? We're going to look at the number of ways to get each, the number of outcomes that give us this many points. So the number of ways to get each event here out of the total number of outcomes. So how many ways are there to get 2 white poker chips? Well, we're doing this in order, so we're going to do them one at a time. The first time you reach in to get a poker chip, there are, how many white ones are there? There are 5 white ones. So there's 5 ways to get the first white chip. And then after that, there will be 4 white ones left. So there's 4 ways to get the second white chip. Then on the bottom here, we're going to put the number of ways to get any 2 chips. So the first time you reach in, there will be 10 chips in the bag. And then when you reach in again, there will be 9 chips in the bag. Okay? And so these are all going to be out of 10 times 9. So I'm just going to go ahead and put that part in for all of these. I'll just make it a little bit faster. Boop, boop. Okay, so white and red. So now here's the thing. You could do white then red, which would be 5 ways to get a white, and then there's 3 red chips, I think. 3 red chips. But you also have to consider that you could get a red chip first and then a white chip. So you can do white and red, or you can do red and white. And that's why I'm adding these two possibilities together here, because you can do one or the other. White then red, or red then white. Either way will get you 6 points. Okay. Now for 2 red, it's just red, red. There's only one way to get the colors in order. So this will be 3 choices for your first red chip, 2 choices for your second red chip. When it comes to white and blue, again, 5 choices if you go white first, 3 choices for red second, but we could go the other way around. Oops, sorry, not red. It's blue, right? But we could also do blue and white. Okay, so that will be 2 times 5. And then the same deal here. We could do red, then blue, which would be 2 times 2, or we could do blue, then red. Right, and then the last one, there's 2 choices for your first blue chip, and then there will be 1 choice for your second blue chip. These are a little more complicated than some of the previous ones that we've done. I am going to simplify these a little bit by actually multiplying together the numerator and the denominator. I'm just going to go through and put equals something over 90 in all of them first, just to speed this up a little bit. Okay, so 5 times 4 is 20. Okay, 5 times 3 is 15. This one is also 15, so this is 30. 15 plus 15. 3 times 2 is 6. 5 times 2 is 10, and another 10, so that's 20. 6 plus 6, that should be 12. And then this is 2. Now, if you want to check whether you did this right, 20 plus 30 plus 6 plus 20 plus 12 plus 2, that should all add up to 90. So let's see if it does. 20 plus 30 is 50, 56, 76, 88, 90. Yep. Okay. Now we're going to do points times probability. And then we'll add that up, and the total will be the expected value. Okay, so I'm doing 2 points times the probability, which is 20 over 90. Remember, this number that's being multiplied by the fraction gets multiplied into the numerator. So this will be 40 out of 90. 6 times 30, 180 out of 90. 10 times 6, 60 out of 90. 11 times 20, that's a little harder, 220 out of 90, I think. 15 times 12, okay. Now it's calculator time. I do not have my times tables up to 15 memorized. 15 times 12, okay, 180. 90. And then 20 times 2, so that's 40, 90. Okay, and now I'm going to add all these up. So I'm just going to add the numerators, and then that will be over 90. Okay, so 40 plus 180 plus 60 plus 220 plus 180 plus 40, 720. And that's over 90. And so if I approximate that with the calculator, actually, is it going to divide equally? Oh, yes, it does. Okay, so it comes out to exactly 8. 8. Okay. So that was the answer to number 10 that I just went ahead and did. Now, here's what's interesting about this. I thought about putting this as number 11. Like, do you notice anything interesting about this answer? So the answer we got for the expected value of pulling 2 chips without replacement is 8. And the expected value for pulling 1 chip is 4. So 1 chip was 4, 2 chips is 8. So you can see here how, what's interesting about this is, like, how can I say this? It's not necessarily obvious that the expected value for the second chip that you take out of the bag is also 4, because you, without knowing what the first chip was. If you don't know what the first chip was, then the expected value for the second chip is actually still 4. And that's kind of interesting. I mean, you would expect that to be true if you were putting the chip back into the bag before you took out another one, but it's kind of interesting that it's also true that that expected value, if you don't know what chip was taken out of the bag, the expected value of the second chip is also 4. And in fact, it'll be 4 for every chip if you don't know what was taken from the bag previously. So something to think about. If you find that cool or interesting, you should probably be a math major. I will see you guys in class.